Hi, I'm Zor. Welcome to Unizor Education. I would like to continue talking about general aspects of functions, what function actually is, what kind of functions you can deal with, and specifically today's topic is monotonic functions. So, very briefly, monotonic means it's basically either increasing or decreasing. It's kind of natural understanding of what this function is about. But let's talk about what it means, increasing or decreasing. First of all, if this is a function, it means there is a domain to this function where the function is defined, and there is a range, there is a codomain. Now, let's ask the question. If I have a function which, for each flower, puts into the correspondence the color, can we talk about increasing or decreasing of this particular function? Obviously not. So what does it mean? The function is increasing or decreasing? Well, first of all, it means that in the domain there must be something which we can talk about as a relationship less than or greater than or equal, etc. Now, the most typical example of this domain is real numbers. So basically, in the mathematics we will be dealing with, mostly we will deal with the functions which are defined on the domain of the real numbers. And among real numbers, we do have this relationship. We can say that one particular real number is less than another. Okay. Now, since we are talking about increasing or decreasing, the same kind of relationship must exist among the values of the function. Now, the values belong to the codomain. They are in the range of the function. So, wherever the function takes the values from, also should be the same kind of relationship. So we can always talk about two particular values of the function. Function of 1 should be less than or greater or equal, whatever, than the value of the function at another point, at another value of the argument. So to define increasing or decreasing functions, we have to have a relationship like this one, less than or greater than or whatever, among the arguments and among the values of the function. And again, the most typical example of such a set which has this type of relationship is real numbers. We can always talk about two real numbers as one being less than another. So, to make the long story short, we are considering right now, when we're talking about monotonic functions, we're talking only about the functions which are defined on the domain of the real numbers and take the values real numbers. Okay, that's done. No flowers, no colors. We're talking about numbers, two real numbers. Now, so, let's just put together the definition of the monotonic function. So the monotonic function is the following. If you have two different arguments, u and v, both belong to the real numbers, both are real numbers, then the value of the function in these two arguments has exactly the same relationship. So if the function is defined at two different points, real numbers u and v, and u is less than v, monotonic function has this property. The value of the function in the smaller number is less than the value of the function in the bigger number. Now, does it mean that the function is supposed to be defined for all real numbers? Not at all. There are some monotonic functions which are defined only on a very, narrow interval or something like this. Not necessarily the entire set of real numbers. Same with values. Not necessarily the function values are covering all the real numbers. It can be a subset. But in any case, wherever it's defined, if we pick two different points from the domain, then the values of the function must comply with this particular inequality. Now, let me ask you this question. Does it mean that this results in this? So, if the function is monotonic, so for any two numbers, one is less than another, the values of the function are in exactly the same relationship. Does it mean that if the value one is greater than another, then the value of the function would be greater in this point than in this point? Absolutely yes. Because u greater than v means v. This is exactly the same. It's equivalent to v less than u, right? Now, from this, using the property of monotonic function, we can say that f at v less than f at u. And this is exactly the same as this. So if one value is less than another, then that other is greater than this one. So basically, if function is monotonic, then not only less than is preserved, but also greater than is preserved. Finally, how about this? What if we will take values which are exactly the same? Well, then obviously we will have to have the same value of the function, just because the function always have one and only one value for some concrete value of argument. So these relationships are preserved always. This is just because it's a function, and these two just because it's a monotonic function. Now, what does it actually mean as far as relationship between domain and the range? Well, the very basic and very fundamental and extremely important property is that monotonic function establishes something which we call one-to-one correspondence. So, domain and the range are in one-to-one correspondence relationship. What does it mean? It means for any one value of the argument, we can find the value among the range, and for any value in the range, we can find one and only one, that's very important, value of the argument. So the first one, that for any point in the domain exists something in the range, that's obvious, because this is exactly the functional relationship. That's the definition of the function. For every element from the domain, from every element from the domain, there is some kind of element in the range. But now we're talking about the inverse relationship. If it's a range, it means it's value of something. So my most important question is it the value of some one particular argument or two arguments are actually mapped to the same value among the range? Now, that is impossible. For a monotonic function, we cannot have two different arguments which are pointing to the same value of the function. Why? Because of this. If these two arguments are different, then one is less than another, which means that the corresponding value of the function should be less, not equal, less than another. So, if we will take any element from the range, which means it's the result of the function applied to something, so that something should be unique. It cannot be the same value. This is impossible for a monotonic function, just because the monotonicity of the function itself. If arguments are different, then because of this, function values must be different, which means for every single point, every single element in the range, there is one and only one element in the domain, function of which is equal to that element in the range. And that's what it actually means, one-to-one correspondence. For every element in the domain, x, we can find the corresponding value of the function, just applying the function itself. But then, that particular element from the range can correspond to only this particular value of the function it came from. There is no other, because other would be less or greater, and the function value will not be the same. So, one-to-one correspondence, that's extremely important for monotonic functions. And one of the consequences of this one-to-one correspondence is existence of the inverse function. So if you have domain to range with a function f, so x goes to f of x. Now, there is an inverse function which always finds what exactly was the element in the domain, the result of which is a particular element in the range. So we have the function which goes this direction, which we will call g. And range. And this function puts into the correspondence for every element in the range some element in the domain, which actually a prototype from which this particular element was obtained using the function f. So we were talking about inverse function before, but this is a perfect example of the case when the inverse function definitely exists. So for any monotonic, for every monotonic function, there is always inverse function. And since we are talking about real values for domain and the range, we are talking about only the function which are defined on the domain of real numbers and take values. The range is also among the real numbers. So both functions f and g are both real values to real values functions. Okay. Now, well, probably would be nice to have some kind of an example. Well, let's have a very simple example. Let's put the function something like this. So, for every element x, real value, we take 1/3 of it, and that's the value of the function. Now, what is the reverse function? Let's just think about it. If we take, for instance, 1, this is x, this is y, we will have 1/3. We have 3, we will have 1. We have 27, we have 9. So, this is the function which is our original monotonic function. It's obviously monotonic. When x is increasing, y is increasing as well. Now, what is an inverse function? Well, the inverse function would put into correspondence to 1/3, 1. To 1, it will put into correspondence 3. To 9, 27. So obviously the inverse function would be this. And it's also monotonic. It's also increasing, because obviously this is true, and from this being true, we basically follow that this is true. Since it's one-to-one correspondence, it means that the reverse function is also monotonic. So, but now these two functions are inverse to each other. Both establish one-to-one correspondence between all the real numbers. In this case, the domain is all the real numbers, and the range is also all the real numbers. And this is just one of the examples. Another example would be, for instance, just give another example. One function would be y is equal to cube root of x, and inverse function would be x cubed. Now, let's just think about it. If we will start with some domain element, for instance, 27. Now, if we will apply this function, we will get 3, right? The cube root of 27 is 3. Now, if we will apply this function now, 3 to the power of 3 would be, again, 27. So, direct function maps number to another number, and inverse function maps this function back to the original. And that's the purpose, basically, of having inverse function. So these two functions are inverse to each other as well. So we were talking about one-to-one correspondence. We were talking about inverse function. Here's an interesting comment which I actually planned. This is my plan, by the way. I planned to mention. So we know that every monotonic function establishes a one-to-one correspondence between between domain and the range, and there is an inverse function. Now, here's my question. Is opposite true? So, if, for instance, we have a function which has inverse function, a function which establishes one-to-one correspondence between domain and the range, does it mean it's monotonic? The answer is no. And to prove it, let me just make the following example. I will use the graph, although we didn't really talk about graphs much, but probably you understand what graph actually means. And here is the graph of the function. I will start with the graph and then we'll derive the formula. So, let's say I'm defining the function only on this particular interval from -1 to 1. And the way how I define it is the following. Here I will define it this way, but here I define it this way. I'll put a little arrow here, which means that at point 0 function is equal to 0 according to this graph. So this is x, this is y. So for every x, to find the value of the function, I have to draw a perpendicular, and this is the corresponding y. Now, this is from -1 to 1 domain of the function. Now, this is, let me just make it a little better here. Don't need this anymore. Okay, this is the range of the function. From 0 to 2. Okay? This is 1, this is 2. This is 1. So, the function is defined from -1 to 1, and for each value x, to find the value of the function, we will draw a perpendicular to the x-axis, to the intersection with my graph, and then to the right or to the left to get the value of the y. Now, is it the function which defines one-to-one correspondence? Oh yes, absolutely. Pick any point here, you will get the point on the y. Pick any point on the y-axis, let's say this point, and then draw the horizontal line until it intersects the graph, in this case at this point, and draw down the perpendicular to x. Now, if it's something else, let's say this is y, then you draw the line parallel to x until it intersects the graph and go down. It's always one particular point. Wherever we pick the y, we will always, drawing horizontal line, we will always intersect our graph in one and only one point, either on this piece or on that piece. So, one-to-one correspondence is established. Now, how about the formula? The formula is y is equal to, on this particular, it's equal to x. This is x, this is y, and they have the same value. If x greater or equal than 0. And this is minus x plus 1. Minus x plus 1 for all x less than 0. So this is the formula which represents our function. It's a formula. It's two different formulas, but it doesn't really matter because these intervals are different. So the whole interval will be covered by these two inequalities. So the function is defined. For any x, I can find the value of the function. Okay, if x is greater or equal to 0, I use this function, this formula, and for negative x, I will use this formula. So I will always find the value of the y. Now, can I find the value of the y? Well, obviously yes, because if my value of the y is below 1, I will use this formula, and if it's above 1, I will use this formula. So basically, the inverse function would be y is equal to x again, if x is greater or equal to 0. And this function, how can I resolve that? Would be 1 minus x, right? 1 minus y. 1 minus x. If x is less than 0. Now, in both cases, x belongs to minus 1, 1 interval. So, the function is defined only within this domain. Or I can put this restriction here, greater than 0 or and less than 1, and here less than 0 but greater than minus 1. That's the same thing. All right, so these two formulas are basically describing my inverse function. So inverse function exists in many cases, not necessarily in the case of monotonic function, because this function is obviously not monotonic. It's decreasing here and increasing there, right? So this is the relationship. Any monotonic function is inversible. Not every inversible function is monotonic. There are inversible functions which are not monotonic. Okay, that's fine. And now there is an interesting aspect of inverse function, which is more about inverse than monotonic, but obviously since every monotonic is inversible, so it's true for monotonic function as well. Let's talk again about the graph of the function. Let's talk about monotonic function and their graph. So again, let's draw our system of coordinates, and let's think about some monotonic function, just as an example, this function. Doesn't matter what's the formula behind it. What is important is that this function, as we see, is monotonic, right? Question is, how will the graph of inverse function look like? That's very interesting. Now, let's think about it this way. Let's say this is the graph of the function y is equal to f of x. Now, if there is one particular point on that graph which has coordinates a, b, now what does it mean? It means that if I will draw down, I will get to the a, and if I will draw across, I will get to the point b. That's what it means. Now, again, it's a little bit ahead of all my discussions about graph, but if you want, you can go there and then return back to this, because it's important property of the inversible and therefore monotonic functions as well. So, if the function belongs to a graph, it means that projections on both coordinate axes are correspondingly a and b. Now, from another standpoint, since this point belongs to the function y is equal to f at x, what does it mean? It means that b is equal to f at a, right? So if I will use the a as an argument, I will get the b. That's what actually means that the function belongs, that this particular point belongs to the graph of this function, right? Now, what is inverse function? Inverse function is the function which, if you take b as an argument, you will get a as the value, right? So direct function takes a as argument and gets b as an argument. Inverse function takes b as an argument, gets a. So if my function is called g, inverse function, if I will take b as an argument, I will get a. Now, from the graphical perspective, it means that if I would like to draw graph of the g function, it means that function with the function g being applied to the point b as an argument, b as an argument, will get a as a value. This is point AB, BA. Right? So if point AB belongs to this graph, point BA belongs to this graph. So always, if there is a one point which has coordinates a and b on the graph of the function y is equal to f at x, and there is an inverse function which can be designated as y is equal to g of x, if we will put b as an argument, we will get as a as a value, and the point b comma a. So x coordinate will be b, and y coordinate would be a. This function belongs to the inverse function, this point. But now let's talk about these 2 points. Points AB and BA. How do they position one relative to another? Well, it's actually very easy. Let's draw a bisector of this angle. So this is 90 degrees, this is 45 degrees. Now, where is point AB? Now, well, the very easy statement in this case is that these 2 points are symmetrical relative to the bisector. Now, it's very easy to prove geometrically, but since this is not a geometry lesson, I would probably refer you to the whole chapter called Geometry in this course. You can try to basically prove it yourself, but believe me, it's very easy to prove that these 2 points are symmetrical relative to the main angle bisector. Which means basically that the whole graph of inverse function would be symmetrical relative to the bisector. So let me again draw, let me try maybe a different color, draw the original graph, which looks like this, approximately, right? And it goes through, okay, something like this, right? This is original. Now, let me draw a graph which is symmetrical to this one, relative to this bisector. Well, it probably looks like this. So these two graphs are symmetrical relative to the angle bisector. This is the original monotonic function, and this is an inverse function. So inverse function always symmetrical with the original function relative to the angle bisector. Well, that's actually all the general properties of the monotonic functions which I wanted to talk about today. As usually, I do encourage you to register as a student, have somebody, or maybe yourself if you want, act as and register as your supervisor or parent maybe. Go to unizor.com and try to take the complete course with all the lectures, exercises, and exams, which is very, very, very important. Good luck. Thank you very much.